being extremely recalcitrant. It refuses to behave, and you seem to never be able to connect to Bluetooth. But the Bluetooth low energy technology is more reliable, and it also uses less energy. So that means you can deploy these in the field through a battery powered for a battery powered application. Zigbee is also another one, widely known, but it also operates on the Wi-Fi band, so you can get some interference. So be careful when you're using it. This is low power, has short range, and low bandwidth applications. If you want to transmit just like let's say this is the battery state or this is the charge state, because you're not actually streaming video, so this is a good, the main part is that this is reliable and it is secure. Security is the biggest aspect in it. This is one protocol that many of you might not be aware of. This is called ANT Plus. Now this is an extremely low power device. It's actually the world's first ultra low power protocol, and it's a framework basically. So I'll tell you, if you actually embed a sensor using the ANT Plus technology inside the wall, and you power it with just those small computer coin cells, just imagine how long it will run. Some guesses, like random. Days, months, how much? Any random guess, anyone? Anything? 1 week, okay. Longer, much longer. How much? Much longer. 3 to 4 years. On just that small coin cell. And it's extremely reliable, ultra low power, and has a very good range. So you might actually want to research a little bit about this, and many cutting edge research in IoT and communication protocols, networks, ECE guys, it's going on this. OCPP. So we work on this. OCPP is Open Charge Point Protocol. So this is a protocol set up, and it's a world standard for use with EV infrastructure. So using this, the charging station will communicate with the energy provider, and you'll have a network of these, and this way, from your mobile app, you'll be able to know where a charging station is located. So all this will be managed through this protocol. And this is a really interesting one. Okay. One question: for for anyone, okay, can we transmit internet using your 240 volt line? Can we do that? Yes, no. How many people say no? Okay, I've put it for a reason, so okay. How many people say yes? Okay, most people don't say anything. Okay, so using this, you can actually transmit data using power lines. So this 240 volt plug, you can plug in a device that will actually transmit broadband data. So I can actually connect a device here, plug in an Ethernet cable, and let's say at the back of the auditorium, there's another plug. I can plug in, put an Ethernet cable, and connect it to my computer and get an internet connection. Yep. So it's called power line communication, PLC. So this is also widely used for communication between the car and the charging station. Also, distribution companies use this protocol to transmit data on the power lines, the big power lines that you see, right? Transmission lines, big towers that are used to transmit electricity. So the power distribution companies use that same big power lines to communicate to local stations how much power they should distribute, or what is the load requirement, stuff like that. Okay, Wi-Fi direct. Okay, can I communicate between, if I have two Wi-Fi devices, let's say this router, another router, this computer is connected to it, but both are not connected to the internet. Will I be able to communicate through them? So many people think no, but you can actually do it because it will make a local area network connection. And there's another protocol called direct Wi-Fi. You can use Wi-Fi as well to communicate through Wi-Fi. Or many, if you might be using those like share it kind of applications, right? So they use Wi-Fi. Cognitive radios. So this is very interesting, and AI guys, open up your ears. So cognitive radios these are actually a network. So you have a network of GSM antennas, okay, the mobile communication. So based upon the demand, how many users are using it in a particular region, and what you also need to take care of the frequency band allocation, you see guys. So this actually manages that intelligently, real time. It will automatically allocate. If one band is very busy, it will automatically allocate to the different band and also manage power. So you're running efficient and also with less power. Okay, why did we go to the last? Okay, let's talk a little about the vision technologies. So this is something very interesting. So CV guys, listen up. Anyone who is interested in CV, so remember mechanical guys, you can also there are many applications of computer vision for mechanics and mechanical engineering. So this is one thing that I think you will find very interesting. So using computer vision techniques, you can amplify the motion of an object. So let's say while I'm speaking, right? So this table might be vibrating very microscopically. So I can actually magnify that motion using computer vision techniques, that very tiny motion, and then recover sound using video only. So I'll just show you the videos, okay? So this is a particular application in which they are actually detecting the pulse of a person.
We can also analyze the frequencies of this signal and extract the heart rate. This doesn't require attaching any sensors to the patient, and the accuracy is comparable with hospital-grade monitors.
So no need for invasive sensors. So as you can see, this is a baby in a NICU. That's for newborn babies and intensive care unit. So you can actually monitor the heart rate of a person, the heart pulse, without actually any physical sensor, just from the video. So our skin color actually changes very slightly when blood is pumped, okay, and the skin tone changes very slightly. So you can actually detect that change, amplify it using Eulerian transformations, and you get more insights you can using your cameras.
The same algorithm can also reveal imperceptible motions, like the pulsing motions of arteries in the wrist. When a person fixates at a point, the eye may move from subtle head motions.
So normally you can't actually see the pulse of your vein, right? Normally, but you can actually amplify that motion and see how the veins are moving. So this is very good. Sorry for people at the back. So you can actually use this technology in medicine for non-invasively looking how your internal organs are moving from the outside, and how blood is actually flowing. You can actually visualize this using this technology. And this is actually quite old. It's like 2013. Yeah. Your eyes actually also move, like they twitch very slightly when you actually fixate on something, when you fixate on an object. So using this, let's say I'm looking, I have a camera, okay, and I'm videotaping all of you. So I can find out how many people are listening to me or looking at me using this, okay.
Such motions are very hard to notice, even in this close-up shot of the eye, but become apparent when amplified 150 times. Invisible motions are also created by mechanical parts, such as the shutter and flipping mirror in the DSLR camera that produce tiny motions when taking pictures.
So you can actually visualize, let's say you're in a factory, you can actually build a tool. So this is actually open source. You can build a tool, and instead of actually looking and going to the particular huge part in a big machine and finding out how it is vibrating, which screw is vibrating, how is it moving, You can use this and find out, okay, this screw is moving a lot, which you couldn't detect or predict using simulations. And with this, you can predict the failure, how the failure rate and when that particular part will fail, and rectify that preemptively.
Structures are designed to sway in the wind, but their motion too is often invisible. Amplifying the changes in this video reveals the swaying of the crane's mast and the undulation of its hook.
Revealing invisible changes in the world. Okay. Let's look at another application. So you can even estimate. Now the possibilities are endless. You in college, okay, when you were in 11th or 12th, you might have done that Young's modulus experiment, determining the strength of a string, or even like guys who do, like you designing a shaft or a chassis, you want to know how strong it is, and what are the properties of a particular material. So using this, let's say I have something very, very deep down in the volcano, or an area where I can't actually go and get that sample. So we can use these techniques to estimate the physical properties of materials.
We present a technique.
So this led to a whole new field of mensuration. So this is called visual vibrometry.
Estimating the material properties of objects with fixed or known geometry.
Also, I would like to point out this is a CVPR paper. So it's one of the top conferences in computer vision. So guys interested in computer vision, you should follow and read what is happening in the computer vision industry.
From small motions in video. Solid objects tend to vibrate at a set of preferred frequencies. These vibrations occur in most materials, but often at scales and frequencies outside the range of human visual perception. However, recent work in computer vision has shown that these vibrations can often be recovered from video, even when motion is much smaller than a single pixel. In this paper, we show that by relating the temporal frequencies of motion in a video to resonant frequencies of visible objects, we can learn about the vibration modes of those objects. And under measured or fixed geometry, the frequencies of these modes can be related directly to material properties. We demonstrate this on several clamped rods and hanging fabrics by estimating their material properties from video. The motion in these videos is very subtle, often much smaller than a single pixel. So to measure the frequencies of this motion, we first calculate local motion signals across the spatial dimensions of our video based on phase variations of a complex steerable pyramid.
So a steerable pyramid it's actually a mathematical it's a mathematical concept. It's kind of advanced. So anyone interested in it, you can go ahead and look at it. I won't explain it. Maybe afterwards, if I have some time, I can discuss it with you. Okay.
Here we can examine the temporal spectra of these local motion signals.
Okay, I won't bore you with these details. Okay, let's move on.
If we present.
Okay. You can even recover sound from video, like I was talking. So this is very good in spy applications. So let's say a minister is giving a speech at the UN, and their team is actually somewhere else. They're actually having an internal discussion. What should be their next move? What should they speak? What are the negotiation strategies? Let's say at the G20 summit that is going to happen right now. So if someone designs a system like that, or if you're a reporter, you can hear what they're doing, but you need a high-speed camera. Why? Because normal cameras, they'll capture information at like about 60 hertz, right? But you need a high-speed camera because the audible range is in 20 to 20 kilohertz. So you need a high-speed camera to capture sound information from videos.
When sound hits an object, it causes that object to vibrate. The motion of this vibration creates a subtle visual signal that's usually invisible to the naked eye. In our work, we show how using only a video of the object and a suitable processing algorithm, we can extract these minute vibrations and partially recover the sounds that produced them, letting us turn everyday visible objects into visual microphones. In the silent high-speed video shown here on the left, we see the leaves of a potted plant shown on the right. The video was recorded while a nearby loudspeaker played the notes to "Mary Had a Little Lamb." Even when we play the video in slow motion here, the vibrations caused by the music are so subtle that they move the plant's leaves by less than 1/100th of a pixel, making the plant appear still to the naked eye. But by combining and filtering all of the tiny motion happening across the image that you see, we are able to recover this sound.
So this is recovered from video. So mind you, they are actually not detecting the changes in the pixel. Let's say if the motion is very minute, like that motion won't be even perceptible in even 1 pixel. That object won't, let's say this moves very little, it won't even move a little, 1 pixel in your video. So how they manage to do this, they actually look at the light that is bouncing off of the material. So if it moves a little, ever so slightly, the brightness and the reflectance, how much light it is bouncing off, it will change. And with that, you can actually estimate how that material is moving. Yeah, so we looked at pulse detection using the changes in the skin color. So this was actually a new discovery. People found out your head actually moves ever so slightly when your heart pumps blood into your head. So with this, they actually discovered this, and you can actually even find out the pulse of a person using the ever so slight bobbling of their head.
In this video, we demonstrate that it's possible to analyze cardiac pulse from regular videos by extracting the imperceptible motions of the head caused by blood flow.
So in future, you can imagine you can extend this research
based on
and let's say detect the blood pressure of a person, or how erratic beatings of the heart. So you can even possibly even detect cardiovascular diseases preemptively. Before you get a heart attack, you can actually detect that heart attack.
And color changes in the skin due to blood circulation. If you've seen someone blush, you know that pumping blood to the face can produce a color change. In contrast, our approach leverages a perhaps more surprising effect. The inflow of blood doesn't just change the skin's color, it also causes the head to move. This movement is too small to be visible with the naked eye, but we can use video amplification to reveal it.
This is the researcher who actually did the research.
Believe it or not, we all move like bobbleheads with different motions at our heart rate, but at a much smaller.
You heard about the Indian bobblehead?
Now you might wonder what causes the head to move like this. At each cardiac cycle, the heart's left ventricle contracts and ejects blood at high speed to the aorta. During the cycle, roughly 12 grams of blood flow to the head from the aorta by the carotid arteries on either side of the neck. It is this influx of blood that generates a force on the head. Due to Newton's third law, the force of the blood on the head equals the force of the head acting on the blood, causing a reactionary cyclical head movement. To demonstrate this process, we created a toy model using a transparent mannequin head with rubber tubes stand for simplified arteries. Instead of pumping blood, we will pump compressed air provided by this air tank, and I can release the air using this valve. Now watch what happens as I open and close the valve once a second, similar to a normal heart rate. Ready? Here. This motion is fairly similar to the amplified motion of real heads.
I think that my explanation is sufficient for you. If you want, I can share these slides. Then you can actually go back and look at these.
We've seen before. In this video, we demonstrate that it's possible.
Okay, so these are the papers that were in the previous slides. You can scan the QR code if you wish to. So this is another one. 3D robotic vision using ultrasonic sensors. So you might have heard people, the Tesla car and many autonomous vehicles, they use LiDAR. You can even use, ultrasonic sensors are the parking sensors in your car. But you can even use a combination, a two-dimensional array of these ultrasonic sensors. So this combines Wi-Fi wireless communication and sensors and computer vision technology all together in one. Also, I'll come to that a little bit later. These sensors can actually vibrate mechanically a little bit. So you also need to be a good mechanical engineer if you want to predict, to take out the noise from the system. So you can use these ultrasonic sensors for imaging. And you can have something like this attached at the end of a robotic arm, and you'll be able to scan that object, detect its pose, how it's oriented, and how it's moving, the texture of that object. And the advantage is that LiDAR actually doesn't work very well in bad weather, and these ultrasonic sensors are cheap, much cheaper than LiDAR, and they don't have these weaknesses. And they're also, but the issue is they're not able to, they don't have very good resolution. So this is the paper that I referred. This is a very interesting thing, and this is, I'll wrap up after this. This is the last one. So you can use Wi-Fi, the routers, and you can turn it into a camera. Yep. So, and with this camera, you can even look behind walls. Yep, I'll show you a video. So you can use this Wi-Fi camera. The same, you can actually even turn the router that you have into a camera. So with this Wi-Fi vision technology, you can actually map your environment, okay, create a three-dimensional mapping of the environment. You can, so some applications, like you can even sense the vital signs of a person, like how they're moving, if they're irritated a little bit, their sleep patterns, something like that. And some recognition-based applications, you can identify if this is a human or not, if this is a chair or something like that. You can even recognize gestures. So if I'm waving, if I'm jumping, doing jumping jacks, and you can even extract information how a person is moving, gait recognition. Like some people like walk a little bit like this, and so you can find out how people are walking. You can also detect how a person is walking, and that might give you some insight into that person. Also, you can recognize if someone is doing some daily activity, and some detection-based applications. If a door is open or not, or where some object is located, things like that. So this is basically a three-dimensional reconstruction after some processing using the Wi-Fi camera. So this is a wireframe, three-dimensional wireframe, how those people are oriented and positioned inside a space. Oh yeah, we'll look at this video.
This video describes a device that can capture the human figure through walls using RF signals. We place our device behind the wall, and it can see the silhouette of a person who walks in an adjacent room. The device works correctly, even if the room is completely closed. For example, if a person stands behind the wall, the device's output looks like this. In particular, the output on the right shows the background in navy blue and the various human body parts in red, orange, and yellow. Here, we can see the person's head, chest, arms, and feet. How does this work? The device operates by transmitting wireless signals that traverse the wall, reflect off the human body, and come back. At every point in time, only a subset of human body parts reflect the signal back to the device. Here, we show the output of the device as the person walks. At different points in time, different parts of the human body reflect the signal, and the device captures multiple snapshots at various points in time. It then combines these snapshots through a reconstruction algorithm that allows the device to recover the human silhouette through the wall.
So even deep learning is also used in this technique. Okay, in some extensions of this technique, if you use deep learning, then you can actually get a better output.
Here, we can see the person's head, chest, arms, and feet. The device can distinguish between different people behind the wall. So for example, over here, we ask two different people to stand behind the wall, and this is the output of our device. By training on different subjects, we can use a classifier to distinguish between them.
So each and every person will have a slightly different register. Even if they have the exact same dimensions, the Wi-Fi signal will actually bounce off a little bit differently from each person. So you can actually, let's say, so this is a potential negative of this. Let's say you're able to train this on the register of a very important VIP person. So you can detect if this is actually the person who's entered the room. So security agencies actually use decoys, duplicates, when they're actually transporting VIP people. So with this, someone could actually figure out, okay, this is that particular specific person. If you train your AI model on this, so AI, you know that AI is very good at classifying things.
Voice can also distinguish between certain human postures. If the person stands straight,
pose estimation, how someone is moving, or how someone is, if I'm picking up a bottle or not, I can do. So this has many robotic applications.
The device can also track human limbs from behind the wall. Here, we show a scenario where a person draws a shape in the air, and we show the output of our device to the right. The device can trace the person's hand.
So the Wi-Fi camera is behind the wall.
We compare the device's output to that of a Kinect placed directly in front of the person.
And this, fun fact, this Kinect camera, it's very cheap now, because you might have known, Xbox actually, this was kind of a flop product, but it was very good for us CV engineers, because we got a very cheap depth camera. So this is a special type of camera. It's called RGBT. So it detects red, green, blue band, and also depth information. So how far a particular object is in the room. And now you can get this for like $2,000-3,000. Even brand new, many refurbished ones are also available.
Show the Kinect's output in red. In comparison to Kinect, our median error is around 2 centimeters. For more information on how the device works, check out our project. Well,
so this is just a news report. I think we can wrap up now. So these are the papers that are there. Thank you. I hope I didn't bore you at all, and hope you found the material interesting, and you'll go back and have a look at it. If you want the slides, I can share it later afterwards with someone, and they can share it with you. Thank you guys.
Now I would like to invite Priyan Sinha sir to continue the session.
Hello again everyone. Unlike my colleague, I'm not going to take lots of time. It will be over in 5 minutes or so. My presentation is on a brief introduction to robotics. How many of you are interested in robotics first of all? Not audible with the last. Not audible. Am I audible right now? Okay. Hello. Am I audible now? Cool. Yeah, so who are interested in robotics? And who all have worked on robotics? Cool. Yeah, so So yeah, I'm sure everyone knows the difference between a robot and a mechanism. Yeah, cool. So I won't bore you all with the finer details of what robot is. I'll straight away go to the divisions of the robots. We have manipulators, mobile robot, drones and hybrid. So hybrid is basically the combination of manipulators and the mobile robots. Yeah, so with each of the divisions, there are a certain set of concepts that is linked with robotics. So for manipulators, there is forward and inverse kinematics. That is, you all know about the degree of freedom of a robot. So how much degree of freedom does this robot arm have? Anyone? If you don't want to speak, just show the fingers. Yeah, it's actually a 3 degree of freedom robot with one end effector. So it's like 4 degree of freedom. So we count it as number of joints. So to calculate the end effector's position, which is the gripper position, we have to calculate the angles of the joint. So that part is called forward kinematics. And given a coordinate that the robot has to reach and calculate the angles of the robot is called inverse kinematics. Similarly goes with dynamics, but dynamics considers the force, torque and all those parameters. Some interesting terms to explore are singularity and move it. How many of you are aware of ROS? ROS is a framework that is used for simulating robots. So my colleague Shirish was saying that nowadays creating a robot is very easy. It has actually become easy because of this these simulations like ROS and move it. You can go and you can hello. Am I not audible to everyone? No? Okay, now am I audible? Yeah, cool. Hello. Okay. Yeah, so the dynamics. Now, yeah. So I was talking about ROS framework. If you are interested to like develop your own robot and try out some algorithms or scripts, you can use the ROS. You can use ROS 2 also, it's trending right now. So yeah, these are the two terms that you should go and search for. So coming to mobile robot, because our company is working on a project on mobile robots. So the robot has 3 basic parts, which is perception, planning and controls. Yeah, before this, like I like to address the mechanical people. Do not feel left out over here because without you all, the robot is not possible, right? So before these things starts, we need to design and analyze all those designs, whether the robot is feasible to ever like move or not. So after those processes, those are the basic things that you need to have. After those things, we can go to the perception. Perception is basically the ears and eyes of the robot. So Shirish might have mentioned about LiDAR. What is LiDAR? How many of you are aware of what is LiDAR? Okay, so LiDAR is a sensor which emits a ray, and the ray the obstructs on the obstacle and it like reads the emitted ray. Sorry, there's a time of flight measurement which you can determine, and on basis of the calculations you can determine how far the object is. So on ROS there's a visualization tool called RVIS. These are the data from RVIS when you're using a 2D LiDAR, a 3D LiDAR and a camera for mapping. So this is done to locate the robot, because I know where I am standing right now. How will the robot know? So robot needs to map this environment and then tell in coordinates where the robot is right now. So some interesting points to note are slam and loop closure. You can go and look it up. Now comes the planning part. Now we know where we are. Now we know where we have to reach. Now how do we plan to reach there? We have obstacles in between. We have some walls and we have to maneuver between them. So these are done by trajectory generation. Trajectory generation algorithms are RRT, A-star and Dyke truss. These are also take care of the collision avoidance. So I'll brief you the RRT working. It's basically the left end is the robot position, initial position, and the right end is the goal. It grows up like a tree, and it weighs each of the leaf of the tree is given some weight. Based on the weights, the robot decides the best route it should follow to reach the goal. That's how the robot reaches the goal. Then comes the control. Controls is a very big and wide field. It also takes care of the controls of the motors, but here we are talking about the controls of the entire system. So the entire system needs to be tuned. The simulation, the problem is everything is very well defined. Gravity is exactly the same. The terrain of the floor is ideal. But in real life simulation, real life, it doesn't work like that. So we need to tune our parameters such as PID controllers. We need to tune the PID coefficients to in order to imitate what's happening in the simulation to in the real world. So similar controllers were MPC. Can you just go back? Yeah, so MPC and adaptive controller. Nowadays, people are using reinforcement learning also as a controller. You can go and look it up because we are short on time right now. I won't be able to explain on that. For the autonomous cars, we use something called as Stanley controllers and Fredette controllers. Yeah, this is just a timeline of the advances of robots. The first robot of that had artificial intelligence integrated in it was made in 1972. The name is Shaky. So artificial intelligence was 1972. It has already been collaborated with robots. Now we are just experimenting with deep learning and RL to see the applications where we can fit in. Yeah, that's all. If you all want to learn, you can just scan the QR and go through it. That will be all. Thank you.
Everybody please gather outside for the photo session with the dignitaries of the event.